Hi, gang. We are starting the last chapter of college algebra, and it is on matrices. One of the applications of a matrix is to solve the systems of equations we just solved in chapter 5 using graphing, substitution, elimination by addition. Another way to solve that is using a matrix. So first, just to get some definitions out of the way here, a matrix is basically a way to organize data into rows and columns. For example, if we have this paragraph, 26 female students and 24 male students responded to a survey on income in a college algebra class. Among the female students, 5 classified themselves as low income, 10 as middle income, and 11 as high income. Among the male students, 9 were low income, 2 were middle income, and 13 were high income. Each student is classified in 2 ways, according to gender and income. This information can be written in a matrix. So looking at the paragraph, it's so, I'd have to read back through it to find exactly, depending on what someone asks me. But if I organize it in a matrix, I can go with females, 5 were low income. Oops. We had 5 as low income and 10 middle income, 11 as high income. Among the male students, 9 were low income, 2 middle, 13 high. Now I have 2 rows and 3 columns. Okay, the rows are listed horizontally, the columns are listed vertically. And it's a little bit nicer way to organize information. Okay, and we're going to use that row column idea to organize data here, okay, and to solve systems. The rows are the first number and the columns are the second number when we talk about the dimensions of a matrix. Okay, so this has 1 row and 3 columns. We call this a 1 by 3. Those are the dimensions. Okay, so look at this one. Think about how many rows, how many columns. The dimensions of this matrix, we have 2 rows and 2 columns. Remember, the columns are vertical. This next one, we have 1, 2, 3 rows. And again, we have 2 columns. It would be called a 3 by 2. That's red for the dimensions of a matrix. And this one, 3 rows, 1, 2, 3, 3 columns. This is a 3 by 3 matrix. Anytime the rows and the columns are equal to each other, we refer to that as a square matrix. Okay, so if you see that referred to in any of the homework or any of the assignments, square matrix means the rows and columns are equal. Okay, a 2 by 2 is square, a 3 by 3 is square, 4 by 4, etc. Okay, now we look at this matrix, okay, some fun pictures. I want you to be able to determine, okay, first of all, let's determine the dimensions of this matrix. 1, 3, this is a 3 by 4, okay? Besides the dimensions of the matrix, we also want to be able to pick out an element of the matrix, okay? So if we label this as matrix A, most of the times we label a matrix by a capital letter, as you'll see on your calculator later. Okay, so then if I would want you to refer to element 1, 3, this is how I would write it. Lowercase a makes me refer to matrix A. The 1, 3, that's not red 13, okay, that's A1, 3. That's the element that is in the first row, third column. So I go to the first row, third column. I know the A1, 3 element is a daisy. Okay, that's how we refer to each element. Okay, if I talk about the A, 3, 1 element, that's completely different. That's the element that's in the third row, first column. So if we were in class right now, you'd be telling me what they were. If you're watching this video, I can't really hear you. So think about, find it, okay, guys? Find it. Third row, first column. Okay, it would be, I'm going to call it waves. Okay, it's right here. Third row, first column. All right, tell me which one the track is. Okay, which one is the track? Think about it for a sec. I hope that you realize that the track is in the second row, third column. So that's A, 2, 3. Okay, see how we label elements differently than if I say, what's matrix A's dimensions? Matrix A is a 3x4. If we use a lowercase a and two numbers right beside each other, that's not 13, that's not 31, that's not 23. This is the element that's in the A matrix, first row, third column. The element that's in the A matrix, second row, third column. Okay? Let's do one more. I want you to find A, 3, 2. You're right. It's the baseball glove. Okay? Third row, second column. All right. Good job. Now we're going to make something with this system. Remember solving systems? Nice 2x2. We can solve this. I get that. But I want to start with something small to show you how to do this with a matrix. The augmented matrix means that I put the coefficients of x and y, and then I make a dotted line, and then I put what it's equal to. Coefficients of x and y as a row, and in the same row, but kind of on the other side of this dotted line, we put what it's equal to. Okay, so I'm taking the x and y out of it. All right, and this is my augmented matrix. This is meant to be 1x minus 3y equals 11, 2x plus 1y equals 1. Our goal, guys, is to get the augmented matrix to look like this. I don't know what the answer to this is. Okay, so I'm just going to put two bogus numbers. Let's say 5, 6. Okay. The reason, think about the reason why we might want our matrix to look this way. Okay, if this is x minus 3y equals 11 and 2x plus 1y equals 1, then this would be read x plus 0y equals 5. This would read 0x plus 1y equals 6. So if I get it to look like this with a diagonal of 1s and a diagonal of 0s, I actually have the answers right here. X is 5, y is 6. So I want to take these numbers and turn them into these numbers. Okay, and I do that by row operations, which we will get into next. Okay, first I'd like you to just practice writing these as augmented matrices. Okay, so take a second. Hey guys, you have to rearrange them. All the x's and y's in the same order on one side of the equals and the numbers on the other. So take a minute and do that. Pause me and do that, and then we'll come back and look at the answers, okay? Okay, hopefully you paused me, and let's look and see if you got the same thing I got. I had to rearrange and subtract y over here and add x over here and make sure my x's and y's are lined up. So my matrix is 1, negative 1, 3, 1, 1, 4, my augmented matrix. This one, I have some gaps, so I have to fill in with zeros. 1x, 2y, negative 1z equals 1. 2x, 0y's, 3z equals 5, etc. Now, this one probably gave you some pause. This has x and y, and this has y and z. Every letter has to be represented in every equation. So I have 1x minus 1y plus 0z's equal 2. 0x's plus 1y minus 1z equals 3. Okay, in order for row operations, which we're going to learn next, to work, we have to have x's, y's, z's, x, y, z's. They have to be, the rows have to represent the same variables. Okay. All right, so let's go backwards. Write these as an augmented matrix. Okay, again, pause me, try them, and we will reconvene. All right, go ahead and try them. All right, gang, this first one, not too bad. And again, I don't care if you use X and Y or A and B or R and S, yeah, whatever you want to use, obviously, as long as you're consistent. I'm just sticking with X and Y. Oh, here's our nice solution matrix, I kind of call it. This is telling me right off, X is 7, Y is 3. 2x plus 5y plus z equals 2, negative 3x. I didn't write plus 0y. Okay, I'm not going to waste my time there. I have to write the 0 when I do a matrix, but when I do an equation, kind of leave it blank. 4x minus 5y plus 2z equals 3. Okay, so hopefully you got those same matrices or those same equations from the augmented matrix. All right. These row operations might not make sense to you at first, but I need you to have this summary. Okay, these are the things that we're allowed to do to rows of a matrix, and we don't change what X, Y, and Z are. Okay, you're allowed to interchange any two rows, not columns. Okay, the way we abbreviate that, like for example, if I was going to interchange row 2 and row 3, I would write this. And then everybody would realize, oh, the way she got to this matrix was she interchanged rows 2 and 3. That's what this IJ notation means, okay? You're allowed to multiply every row by the same non-zero, of course, real number. Okay, and the way I show that, if I'm going to take row 1 and multiply it by 5, I would just write this. And then people would realize how I got from one matrix to the other was I multiplied row 1 by 5. Okay, notice they write this sometimes too to mean I multiplied 5 by row 1 and I got a new row 1. Okay, again, you understand this better when we get to actually doing an example, and we're allowed to add to a row a non-zero multiple of another row. So in other words, I could take 2 times row 3, add it to row 2, and that would be my new row 2. Okay, that's what this means. If I would see this notation, I know I took 2 times row 3, added each entry of that to row 2, and that's how I got my new row 2. Okay, this last letter is the new row of the new matrix. All right, let's try some row operations. Okay, our goal is to do all the row operations and get it down to the final, our final thing should look like this. Let's just say if I have a 3 by 3, 0, 1, 0, 0, 0, 1. And then we'd have, I don't know what numbers would be here, 2, 5, negative 6. That would mean X is 2, Y is 5, Z is negative 6. Okay? So what we do is we want to start out getting a 1 in this upper left corner. Then we want to get all the zeros underneath it. Then we want to get a 1 in the second row, which would be here. And then we get the zeros above and underneath it. And then we get another 1. And then we get the zeros. So that's how you have to go through the steps so that you're not undoing steps along the way. Okay? You get the 1 and then zeros. You get the next 1 in the next column, and then you get the zeros. You get the next 1 in the next column, and then you get the zeros. Okay? You always have to start getting 1s first, and then get the zeros. Then you get the 1, then you get the zeros. All right. We will solve one in the next video.